Okay, so let's take a look at 6.1. So in chapter 6, generally, what we're going to be doing is solving trig equations. So in chapter 5, we were focused on verifying trig identities, and trig identities were things that were true regardless of the angle that you plugged in, for x or theta or whatever it was. But then you can also have trig equations, which are not necessarily true for every single angle, but could be true for certain angles. And so we want to get a good technique for solving for those angles. And so that's what we'll be doing in this chapter. Now, before we get to actually do that, we need to talk about the inverse trig functions, which we've kind of explored a little bit in the past, but we're going to talk about them in a little bit more detail now, because a lot of the time when we're solving a trig equation, we solve it by taking an inverse trig function in order to solve for the angle. So we need to get a good handle on how the inverse trig functions work. So let's do that. So first of all, just in general, the idea behind an inverse is that an inverse function undoes the original one. So if f of a equals b, then it should be the case that f inverse of b equals a. Now, because of that, only one-to-one functions have inverses. And so you may remember from your algebra days what it means for a function to be one-to-one. So for example, f of x equals x squared is not one-to-one. It fails the horizontal line test. And the reason it's not one-to-one is because you can have two different inputs that give you the same output, right? So like f of 2 equals 4, but f of negative 2 also equals 4. And so the reason that causes a problem with inverses is because now if you ask yourself, what's f inverse of 4? Well, you don't get a unique answer, right? It's like f inverse of 4 could be 2, but it could also be negative 2. And so it's not well defined in the sense that it doesn't just give you a unique answer. So we don't like that. Okay, and so we don't have inverses for functions that are not one-to-one. Now f of x equals x cubed, on the other hand, is one-to-one. So for each output, there's only one input, right? There's a unique input. So there's no issue defining f inverse of 8, right? It's like we know that f inverse of 8 has to be 2. F inverse of negative 8 would be negative 2, right? Same thing goes for any other like output, I guess. Okay, well, so what does this have to do with the inverse trig functions? Well, you may recall from our graphs of the trig functions that we looked at that not a single one of them is one-to-one, right? None of the trig functions are one-to-one. One way that you can see that is for example, sine of pi over 3 is root 3 over 2, but so is sine of 2 pi over 3, right? That's also root 3 over 2. And sine of 7 pi over 3 would also be root 3 over 2, and so on and so forth. In fact, there's infinitely many angles such that sine of that angle is equal to root 3 over 2. So if you're asking yourself, what is sine inverse of root 3 over 2? It's like you'd have infinitely many possibilities, right? So to get around this difficulty, we define the range of our inverse trig functions so that we get unique outputs for them. Okay, so and then I'm going to show you this chart from your book, if I can get the dot cam oriented correctly. Okay, so this is on page 259 of your textbook, and this gives you all of the kind of standard domains and ranges. Well, really the standard ranges of your inverse functions. So, for example, for the function sine inverse of x, the range is going to be from negative pi over 2 to positive pi over 2, right? So you're in quadrants 1 and 4. So sine inverse of x, we define it so that it only gives you inputs in quadrants 1 and 4, okay? Cosine inverse is defined so that you only get outputs in quadrants 1 and 2, right? So the range is 0 to pi, and so on and so forth for the rest of them, okay? So this would be a good chart to memorize, right? The ranges of these inverse trig functions. It's very important to memorize those, and let's talk about why. Okay, so the reason that it would be good to memorize those things is because if you're looking at, for example, sine inverse of 1/2, Um, so there are infinitely many angles such that sine of that angle is equal to 1/2. So how do you decide which one of the angles is sine inverse of 1/2? Well, it's the angle that lives between negative pi over 2 and pi over 2. Okay, and there's only one of those, right? So for example, pi over 6, sine of pi over 6 is equal to 1/2. So sine inverse of 1/2 could be pi over 6, but then again, sine of 5 pi over 6 is also equal to 1/2. So sine inverse of 1/2 could also be 5 pi over 6. How do you decide if sine inverse of 1/2 is pi over 6 or 5 pi over 6? Well, you look at which one of those angles lives between negative pi over 2 and pi over 2, right? And pi over 6 is the one that lives in that interval. Okay. All right. So that's why it's so important. That's why it's so important that you memorize the ranges of the inverse trig functions so that you know which of all of the possibilities actually lives inside of the range that you're interested in. Okay. So in a similar way, right, cosine inverse of 1/2 means, cosine inverse of 1/2 equals b means that cosine of b equals 1/2, but it also means that b is between 0 and pi. And so there's only one solution. There's one unique solution, and it's pi over 3. Even though, so 7 pi over, right, cosine of 7 pi over 3 would also be 1/2, but 7 pi over 3 is not between 0 and pi. Was that right? Is that what am I thinking of it? Not 7 pi over 3. So 5 pi over 3. Sorry, not 7 pi over, well, 7 pi over 3 as well. But I was thinking of 5 pi over 3. 5 pi over 3 is in quadrant 4. And cosine of 5 pi over 3 is also 1/2, but it's not between 0 and pi, right? So only pi over 3 satisfies both of these conditions. And you get the second condition just from that chart that I showed you. Another thing that I want to say notationally is this. So sometimes the inverse trig functions are denoted with a little arc. So instead of calling it sine inverse, they'll call it arc sine. Instead of cosine inverse, they'll call it arc cosine. But they mean exactly the same thing. Okay, so they mean just exactly the same. Okay, so let's go through a few examples. And by a few, I mean I've got a whole bunch. I'm not even going to count them. But here we go. So let's evaluate the following without a calculator. See if we can do these in our heads. So cosine inverse of root 3 over 2, go ahead and give the video a pause, see if you can figure that out. You should be thinking of what angle, cosine of what angle equals root 3 over 2. And the angle has to live between 0 and pi. Okay, so see if you can work that one out. Okay, so I think this is going to be 30 degrees, or I don't know if we're giving these in let's give them in radians. So 30 degrees would be pi over 6, right? Okay. Let's do cosine inverse of negative root 3 over 2. Okay, so for cosine inverse negative root 3 over 2, now cosine inverse maps us between 0 and pi, so quadrants 1 and 2. So this angle has to be in quadrant 2. And its reference angle has to be pi over 6, so I'm thinking 5 pi over 6, right? So 5 pi over 6 is that one. Now contrast that with sine inverse, right? So let's do sine inverse of root 3 over 2. Or maybe better yet, let's do sine inverse of 1/2. Because sine inverse of 1/2 is also pi over 6, right? We just talked about this. And so then that might lead you to think that sine inverse of negative 1/2 is going to be 5 pi over 6. But you'd be wrong, okay? Because cosine inverse maps between 0 and pi, but sine inverse maps between negative pi over 2 and pi over 2. So the answer is not 5 pi over 6 because 5 pi over 6 does not live in the appropriate interval. Okay? So give it a pause, see if you can figure out what sine inverse of negative 1/2 should be. So sine inverse of negative 1/2. Remember that sine is an odd function. So sine of pi over 6 equals negative sine of negative pi over 6. So in other words, right, sine of negative 1/2 should be negative pi over 6. Okay, and negative pi over 6 lives in that interval. It lives between negative pi over 2 and pi over 2, and that's why that's the correct answer, and not 5 pi over 6. Even though, well, I guess sine of 5 pi over 6 wouldn't be negative 1/2 anyway, but you might think, like, what about 7 pi over 6, right? So sine of 7 pi over 6 is negative 1/2, that's true, but 7 pi over 6 doesn't live between negative pi over 2 and pi over 2. Only negative pi over 6 does, and so that's why sine inverse of negative 1/2 is negative pi over 6. Okay, let's do this one. This is kind of fun. Tangent inverse of tangent of pi over 3. Okay, give the video a pause, see if you can work that one out. Okay, here's my solution. So I'm just going to do this one piece at a time, right? So tangent of pi over 3, let's see. So that's sine of pi over 3 over cosine of pi over 3. Sine of pi over 3 is root 3 over 2. Cosine pi over 3 is 1/2. So that's just going to be root 3, right? So this is tangent inverse of root 3. And now to figure out what's tangent inverse of root 3, we have to work backwards, right? So we have to think, now tangent inverse maps us back to from negative pi over 2 to pi over 2. Okay, so this angle has to be between, so we have to find an angle such that tangent of the angle is root 3 and the angle is between negative pi over 2 and pi over 2. Well, pi over 3 will do the trick, right? So tangent inverse of root 3 is just pi over 3. And so you might think, well, of course, right? The inverse trig function cancels off the regular trig function, and you just get the angle. And that is true most of the time for inverse functions. However, because the inverse trig functions are not true inverses, they're only inverses of like a little portion of the graph, this relationship doesn't always work out. And let me show you that is in fact the case. So let's do tangent inverse of tangent of 2 pi over 3. Okay, give the video a pause and see what you get. Okay, so here's my solution. 2 pi over 3 it has the same reference angle as pi over 3, so I know that the value is going to be root 3, so this is going to be tangent inverse of plus or minus root 3. I just have to decide if it's positive or negative. Now 2 pi over 3 is in quadrant 2, and tangent is negative there, so this would be tangent inverse of negative root 3. Okay, now here I run into an issue, because if I just say that tangent inverse of negative root 3 is 2 pi over 3, I'm going to be wrong, okay? Because 2 pi over 3 does not live between negative pi over 2 and pi over 2. And that's where tangent inverse is supposed to map to, right? It's supposed to map between negative pi over 2 and pi over 2. So I have to think of a different angle. I have to think of a different angle such that tangent of that angle is negative root 3, and the angle lives between negative pi over 2 and pi over 2. So I know that the reference angle has to be pi over 3, okay? And then, just like my reasoning up here with the sine function, it's like I know that sine is an odd function. Tangent is also an odd function. So, so I'm thinking this is going to be negative pi over 3, okay? And in fact, that is the correct answer. So, the main point of showing you parts E and F is just that 2 pi over 3, we had tangent inverse of tangent of 2 pi over 3, but the answer was not 2 pi over 3, okay? It was negative pi over 3. These things only cancel and leave you with this angle if this angle is in the range of the inverse function, okay? And 2 pi over 3 is not in the range of the inverse function, so we have to think of a different angle. It has the same reference angle, though. It's just you have to get it in the right quadrant, okay? In the right range. So in the case of tangent inverse, it has to be between negative pi over 2 and pi over 2. In the case of cosine inverse, it has to be between 0 and pi. Okay. Okay. A couple more, just to kind of show you that you could have some nonsense sometimes. Arc sine of -1. So try to think of an angle such that sine of that angle is -1 and the angle is between -π/2 and π/2. Okay, you should have come up with -π/2. Okay, that's the correct answer there. Arc sine, like we said a second ago, is the same thing as sine inverse. Whoops, sine inverse. So arc sine and sine inverse, they mean exactly the same thing. And yeah, sine of -π/2 is -1. Okay. But let's say that you had something that said arc sine of -2. Now for that one, you should just get undefined, because sine lives between -1 and 1. So sine inverse, the inputs have to be between -1 and 1. -2 is outside of the range of the sine function, so this thing is undefined. Okay, so that's that. Let's practice using our calculators now. This is a little easier, so let's evaluate with a calculator. I'll let you do arc cosine of 0.7, and then arc secant of 0.7. So go ahead and give the video a pause and see if you can work those out. We've done these kinds of things in the past, I think. Okay, so arc cosine of 0.7 in radians, this would be about, maybe I should say about, so approximately 0.795 radians. In degrees, this would be about 45.6 degrees. Okay. Now, what about the arc secant of 0.7? That's a little trickier, because chances are you don't have a secant inverse button on your calculator. Okay, so so we have to remind ourselves, right? Let's say that this thing equals x, right? So we're saying secant inverse of 0.7 equals x. That means that secant x equals 0.7, and that x is between, oh, for secant, we're between -π/2 and π/2, I believe. No, 0 and pi. Yes, because secant's 1 over cosine. Anyway, so we should be between 0 and pi, but your calculator will do this anyway. What I want to show you is this. So secant x equals 0.7. That means cosine x equals 1 over 0.7. And then you take cosine inverse of both sides. So x is cosine inverse of 1 over 0.7. This is something that on your previous test a lot of you did wrong. Okay, it's not 1 over cosine inverse, right? This is not equal to 1 over cosine inverse of 0.7. It's cosine inverse of 1 over 0.7. So don't do it this way, do it this way. Okay? All right, let's see what we get. Oh, it's of course it's undefined. 1 over 0.7 is 1.42. That's oh yeah, of course it's undefined, because secant, the range of secant is between is -infinity to -1, and then from 1 to infinity. This is right in the sweet spot where it's undefined. Maybe let's change this to 1.7, just so that we can finish the problem. Okay, let's try it again. Okay. Okay, so in radians, this would be about 0.942, and in degrees that would be about 54.0. Okay. Very good. Let's try. Okay, so let's try this. Let's evaluate sine of cosine inverse of -3/5. And let's do this without a calculator, okay? So I don't want you to just plug this into your calculator. Let's see if we can do this by hand. So, okay. Now, we don't know an angle such that cosine of that angle is equal to -3/5, right? We don't know that off the top of our heads. But we may not need that, right? Because here's what I'm going to do. I'm going to say let theta equal cosine inverse of -3/5, right? So then what we really are looking for is sine theta, right? Okay, because cosine inverse should map back to an angle, right? So I'm calling this, I'm just calling this whole thing theta, right? So we're really looking for sine theta. Well, if theta equals cosine inverse of -3/5, then that means that cosine theta is -3/5, and theta is between 0 and pi. Or if you prefer degrees, you could say it's between 0 degrees and 180 degrees, right? That's how I'm going to think of it, because I'm about to draw a right triangle. Okay, so or at least a reference angle. Now, if cosine is negative, then we can be even more specific and say theta must be in quadrant 2. Okay, so there's theta, and cosine theta is adjacent over hypotenuse, right? -3/5. Now we can solve for the missing side. This is a 3, 4, 5 triangle. You can use Pythagorean theorem to get the 4, I guess, but I just know from experience that's going to be a 4, right? So that's a 3, 4, 5 right triangle, and so now we can find sine theta pretty easily, right? So I'll say sine of cosine inverse of -3/5 equals sine of theta, and sine of theta is 4/5, right? Opposite over hypotenuse, 4/5. And that's that. Okay, let me give you a couple more kind of like that so you can work on them. Okay, so let's do tangent of arc sine of -12/13. So go ahead and give the video a pause, see if you can work that one out. Okay, here we go. So I'm going to call this thing theta, just like before. And so what I'm really looking for is tan theta. Okay? Well, if arc sine of -12/13 equals theta, then sine of theta equals -12/13, and theta is between pi/2, so I'll call it -90 degrees, and +pi/2, so +90 degrees. Okay. Now if that's the case, then since sine theta is negative, theta must be down here in quadrant 4. But theta is not this angle going all the way around. Theta is a negative angle. It's this angle right here. That doesn't make a huge difference in your calculations, but anyway, I just thought I'd point it out, right? Theta is this negative angle. Okay, sine theta is opposite over hypotenuse. If you solve for the missing side, you can use Pythagorean theorem. You should get 5. Right? This is a 5, 12, 13 triangle. Okay. So then tangent of arc sine of negative 12 thirteenths equals tangent of theta. And tangent theta is opposite over adjacent. That's negative 12 fifths. And that's that. Okay. Very good. And one more. This is kind of a fun one. Let's do cosine of arc tan root 3 plus arc sine 1/3. Okay. Now I'll give you a hint. Here's what I would do. I would maybe call one of these things u and call the other thing v or something. Or you could use theta and phi or whatever, right? But this is really just cosine of u plus v. And you can use your trig identities, right? Cosine u plus v, or maybe we could have just called them alpha and beta, right? Anyway, that's going to be cosine u cosine v minus sine u sine v, right? Okay. So let's draw our little right triangles, right? If arc tan of root 3 equals u, then tangent of u equals root 3, and for the arc tangent function, u has to be between negative pi over 2 and pi over 2. Or negative 90, positive 90, whatever, however you want to say it. Okay. And then if arc sine of 1/3 equals v, then sine of v equals 1/3, and sine maps to the same region. Oh, not u, v. Sorry, v. For the tangent, I'm not using equal signs because tangent's not defined at negative 90 and 90. It has asymptotes there, right? But sine is. Anyway, so angle u. Tangent is positive, and so we must be in quadrant 1. Right, so there's u. And tangent would be opposite over adjacent. Then we can solve for the hypotenuse. So 3 squared is 3, 1 squared is 1. That's 4 squared of 4 is 2. So this should be 2 over here, right? And v, sine of v is positive, so again, we must be in quadrant 1. There's v. Sine of v is opposite over hypotenuse. So 1 squared plus something squared equals 3 squared. So 1 plus something equals 9. So the something squared equals 8. So square root of 8 is 2 root 2. This should be 2 root 2. Okay, this is v. Very good. So let's see. Cosine of arc tangent of root 3 plus arc sine of 1/3 equals cosine of u plus v equals cosine u cosine v minus sine u sine v. And now we know what that equals, right? Cosine u is adjacent over hypotenuse. Cosine v is adjacent over hypotenuse. sine u is opposite over adjacent, and sine v is opposite over, sorry, not opposite over, opposite over hypotenuse. I said the wrong thing, wrote the correct thing. Sine v is opposite over hypotenuse. Okay, and so putting all that together, the 2 here will cancel 2 there, although I kind of want to get a common denominator so I can rewrite this all as the same thing anyway. So we've got 2 root 2 minus root 3 all over 6. So kind of interesting, right? Kind of interesting that you can do this nastiness. Very good. Okay. So a couple more examples, and then we'll call it good for this section. But let's rewrite as an algebraic expression. So sine of tangent inverse of u. When we say to rewrite it as an algebraic expression, what we mean is we want to eliminate all the trig stuff. We just want to have, like, you know, addition, subtraction, multiplication, division with, you know, the variable u. Maybe some radicals, whatever, right? But no trig functions. So see if you can rewrite that as an algebraic expression. Okay, uses the same trick as what we've been using. I'm going to call tangent inverse of u theta. And so what we're really looking for is sine theta. If tangent inverse of u equals theta, then tangent to theta equals u, and theta is between negative pi over 2 and pi over 2, right? Okay, now, so there are kind of 2 possibilities, I guess, right? So it could be, because we don't know if u is positive or negative, so it could be, in the case of tangent, it could be that you're either in quadrant 1, so maybe theta's there, or it could be that you're in quadrant 2, like this, so theta is that negative angle there. We don't know which one. However, in both cases, tangent theta is u, that's opposite over adjacent, or in this case, opposite over adjacent. Okay, and then if you solve for the missing side, you're going to get u squared plus 1 squared equals that side squared. So u squared plus 1 equals this squared. So this equals the square root of u squared plus 1. So right here is the square root of u squared plus 1. And you're going to get exactly the same thing down here, right? This is just going to be the square root of u squared plus 1. And so notice that in either case, sine theta is opposite over hypotenuse. That's u over square root of u squared plus 1. Or opposite over hypotenuse, u over square root of u squared plus 1. Okay? So sine of tangent inverse of u is always just u over square root of u squared plus 1. And that's all there is to that. So, so that's kind of nice. Let me give you one more example of that. It's a shame I have to start a brand new page to do one last example, but I wanted to show you this one because it also uses a trig identity. So let's say that you were confronted with this. And again, your goal is to rewrite this as an algebraic expression. If it was just cosine of sine inverse of u, you could do exactly the same thing as what we did before. But the 2 kind of messes things up a little bit. So here's my suggestion. I would say call sine inverse of u theta. Right, so call this thing theta. So then what you're really looking for is cosine of 2 theta. Okay? because cosine of 2 theta, you can use a trig identity and rewrite this as something like 1 minus 2 sine squared theta, right? That was one of the trig identities. And the nice thing about this is that if sine inverse of u equals theta, then sine theta equals u. So you can replace sine theta here with just u, right? So this is just 1 minus 2 u squared, and that's it. So that's kind of nice. Anyway, that's all I have for 6.1. Starting in the next section, we'll start solving some trig equations.